Hi, it's Robin. I've got here a Commodore 64 tape I've never seen before, titled CBM-64 Fix by a company called Technicom. And all I know about it is what it says on the label. This is an official Commodore program designed to solve a problem on certain CBM-64s. And that was the early name for the Commodore 64. Load, fix, and then run if data doesn't print to screen correctly on your computer. That description makes me think of the kind of infamous kernel version 2 bug in earlier Commodore 64s. So I've made videos about the different kernel revisions before. This is a computer I don't use very often, but I have shown it before. It's not my favorite one because the video output isn't great, and the keyboard's not as good as some of my other computers, but this is my best kernel version 2 Commodore 64. And the way you can tell a kernel version 2 computer, as I've explained before, you can just peek location 65408. And if it returns a 0, then you have kernel version 2. If it returns a 170, that is AA hex, then you have the even earlier kernel version 1. And if it returns a 3, then you have kernel version 3, the final and by far most common kernel version that has all the bug fixes included. Kernel version 2 is actually probably the buggiest of them all. Version 1 was even better. I don't know what they were thinking. But the biggest flaw, and that's what that tape label alludes to, is if you poke to the screen, 1024 is this top left corner up here, the memory location for it. If we poke a 1 in there, an A should appear, but nothing appears there. On kernel version 1 or kernel version 3, we would see an A in the top corner. But if we move up there, you'll see there is an A. It's just printed in the same color as the background. So it isn't until we flash the cursor on it that it shows the contents. So based on this description, it sounds like this is a fix for this specific problem. And I'm very familiar with it because my first Commodore 64 was a kernel version 2, and quite a few type-in games and so on would not work properly because of this bug. It's weird that it says it's an official Commodore program because I have never seen this, and I don't know, like, you'd think if it was official, it would have been distributed more widely. They would have included it maybe on that 1541 disc that got circulated a lot. I don't know. If it's official, why isn't it on a Commodore tape? Why is it on this Technicom? Okay. And I looked up this Technicom. Seems like it was a telecommunications company that sold telephone equipment. And it even seems like they had a bit of a multi-level marketing kind of thing going on. I don't know. Anyway, way more than enough talking. Let's try this out. So I'm just going to reset the computer. I've got Kung Fu Flash with the super snappy ROM version 5.34 update. But I'm just going to disable it for now, but we're going to use it more later. And I do have my SD to IEC hooked up back here, which I'm going to try and save this tape onto just so it's preserved. Okay, so just like any tape program, we'll type load. We'll press play on tape. And we'll see if this program loads. Okay, found fix. We'll load it. Press the Commodore key. Ready. Okay, quite a short program. Let's list it just to see. Okay, it looks like it's just a machine language program with a single sys command, 2063. It's from the future. Okay, let's just try running it and see. Okay, ROM enhancements in place. I guess enhancement number 1, poke to screen RAM. That's just what I was showing you. I guess that means it's fixed. And number 2, 0 is less than or equal to free 0, which is less than or equal to 38909. Okay, these are really cryptic enhancements, but this seems that in addition to fixing the screen poke bug in kernel version 2, it's also fixing the free command. And that's kind of broken-ish on all Commodore 64 revisions because that's part of the basic ROM, and they never updated the basic ROM throughout the life of the Commodore 64. The same ROM that shipped in the very first 64 was still there in the very last C64. It's just that recent video where we were optimizing that bouncing program. I was using free all the time, and over again, I had to type this kind of cryptic command in. So with this fix in place, there, print free 0 properly returns 38909 bytes. And as I showed in that previous video, normally it returns something like 26617, or what is that? I typed it in about 100 times in that episode. I've mentally blocked that out. So that's pretty cool. This program fixes 2 things. And one other neat thing is it even survives is if I hold down stop and restore, usually that resets the computer, all the various vectors, but it's pretty cool. The patches actually survive. Poke 1025, comma 2, should put a B up. There it is. Okay, so that's the patch, and that'll be available as a download in the video description if you just want to try that out yourself. But of course, I'm not going to stop there. I was curious, how does this program work? I've gone ahead and disassembled this. There's going to also be a D64 available for download. And if we load the first file, COM8, 1, or use a percentage sign with Super Snapshot. Okay, so I've got Turbo Macro Pro here. And what I've done is resourced. So I disassembled this program and have turned it into source code so we can look at it. Should be easier to understand this way. Okay, so we'll look through the source code here. I'm not going to explain absolutely every last thing as if you don't know anything about 6510, but I'll just highlight some things, and some of this I've been over in many previous episodes. So the program does use a little bit of zero page, so I've just called that label, this is just my habit, ZP1, zero page being the first 256 bytes of RAM in any 6510, 6502 system. And the basic ROM is located at 8000 hex and the kernel ROM at E1000. Those are going to be copied from ROM into the RAM underneath. And the length of the ROM is 2000 hex bytes or 8 kilobytes worth. Okay, the program assembles to 0801, just like any basic program. And just in recent episodes, I've been over this basic stub before. This is basically building up a line of basic that we saw, line 10, sys 2063, and it's just recreating that in assembler, and by putting this at the beginning of our program, we're making it a basic stub that allows the program to be runnable even though it's a machine language program. And again, I didn't write this. This is an old program. This is just my recreation of the original source code as best I can do it or imagine it. Okay, and that address 2063 is this code right here that I've called startml, start machine language. And I've added comments that I think are correct. If I'm wrong, then feel free to correct me. We're going to set up to do a copy from ROM to the RAM underneath, disable interrupts, and loading the 16-bit pointer to the beginning of the basic ROM, and storing it in that zero page location, low byte and high byte. And then this loop copies one page, that is 256 bytes, from zero page 1 to zero page 1. Now, that might look like it's not doing anything. You're just loading and storing something exactly in the same place. But on the C64 architecture, loads come from ROM, unless the ROM is switched out. But the load will come from the ROM, but when you store, the C64 automatically passes that byte through to the RAM underneath, because storing to a ROM doesn't make any sense anyway. So what this is doing is just storing the ROM in exactly the same location in the RAM underneath. And this is a deliberate C64 feature. I know some people say, oh, this is so inefficient. What a waste of RAM. Well, most of the time you're not using it for anything else anyway, not on most basic programs. And if you have a better way of patching it, you go right ahead. But this is a simple, straightforward way of doing it that a lot of C64 programs would do. Y starts at 0. It copies 256 bytes here using indirect indexing. And then it increments the high byte of the pointer. Has it reached the end, that is the start basic ROM plus the length, the 8K. And if it hasn't, then it does another loop. So it'll copy 256 bytes at a time. That's the limit with this 8-bit processor. And then it'll keep copying 8K, 32 pages in total once it reaches the end. That does exactly the same thing for the kernel ROM, except, of course, starting at E000, which is what this label is. And then again, does a copy. This is not the most efficient copy. I think I did a much shorter one in a previous video, but that's okay. Again, I didn't write this. I'm just explaining how it works. So it does exactly the same thing, copying the ROM. So now we've got both the basic ROM 8K and the kernel ROM 8K copied to the RAM underneath. Now we're going to twiddle location 1 is the input-output port on the 6510 processor. That's really the only difference between a 6510 and a 6502. It has this additional I/O port, 6 bits. And on the C64, 3 of those bits are used to control the memory configuration because, yes, there is 64K of RAM, despite what the specky users will say. And there's 20K of ROM, plus there's I/O. And this will just switch out the ROMs and reveal the RAM underneath. But because they're identical, the computer will just continue to operate as before. Okay, next we're just going to patch the kernel ROM. So this is just a series of bytes. These are all opcodes. This is like load A with 1 and storing them in these locations. And then those 4 bytes are sequential. And then this last one is in a different location. So those are 5 bytes total patched in the kernel ROM. And we're going to get into much more detail about what they're doing next. Just for now, just know that it's just tweaking 5 bytes there. And there's a patch to the basic ROM where it's actually going to load them from this table called patch. That's 11 hex or 17 decimal plus the 0 index. So it's actually copying 18 bytes from this table patch into this location in memory. And then it's just doing some more individual bytes here. 3 more bytes. I can see that 4C is a jump. So it's probably patching a jump in fact, BF53. That's exactly this address here where the bigger patch is. So basically there's an 18-byte patch in one location and a 3-byte patch later. Again, we'll get into the details in a bit. The last bit here, interrupts are re-enabled. They were disabled because you didn't want an interrupt happening while your kernel ROMs are out and being modified. Just safer that way. And then finally, the screen is cleared. 93 hex is the PETSCII code for clear screen. So just prints it. I do not know why that BPL loop 3 is. That is never going to be true. Branch of plus, that would be if the high bit was 0. Yeah, I really don't know why. Because this is set, so therefore this won't happen. Pretty weird. If anybody has a good idea why that would be in there, I would assume it's just old debug code or old code that they never got rid of. Then we actually print that clear screen. That clears the screen. Load Y with 0, and it's just an index into this string. That's going to print, and that's that message. Prints it character by character. Increments Y. Right here, it's checking for a null byte, a null terminated string. And increment Y. Branch if not equal. That's actually like a branch always, back to loop 4. If the string was 256 characters, it would exit, but it's not. Okay, then this is a basic routine that calls new and restore and just kind of resets the computer after the patch is applied. That might be handy for your own programs. And then finally, The clean way to exit to basic after writing a program like this is this: jump A474. That prints the ready prompt and exits. All that's left in the program are those two tables that we referred to. Here's the string that prints out that message about ROM enhancements in place. And that's just that text message that we already looked at that shows in a rather cryptic way what has been enhanced or fixed. Here's the machine code for that basic patch, and we'll be looking at that in more detail later. Okay, so there's that program. Okay, so that's how the patch does its magic, but we haven't looked at the actual patch, which is kind of cryptically hid. All these different hex bytes are the machine code that was poked in to modify. So we'll look at that next. So if I reset the computer. Okay, I think I forgot to actually show on camera saving that file, but here, I've saved it as fix3. Probably just be called fix on the disk. Okay, if I run. Okay, so those enhancements are in place. Let's use the machine language monitor here. I'm just going to press the special button, which is freezing, which enables the super snapshot. And we'll go into the machine language monitor here. So if we put a 3.7 in location 1, that's what that does. That's going to ensure that the ROMs are in place right now. So let's just go through those different patches. I'll show you the before and the after. Okay, so this is one of the spots that's patched in the kernel. This is where the 4 bytes are going to be stored. So this is the original. And if we change location 1 to 3.5, that will switch the patched RAM in underneath. And I will just disassemble exactly the same code now that the patch is in. And if we compare here, this is where the difference is. Okay, so what this part of the kernel does is prints a blank line, whether the screen has scrolled, like whether you cleared the screen or you scroll the screen, it needs to print a new blank line at the bottom of the screen. This is the routine that does it. 27 hex is 39 decimal. Yeah, I think I went over this in detail in a previous video about an input bug on both the VIC-20 and the Commodore 64. But these routines do a bit of math to set up some pointers, and then this is where it just loads 20 hex, that's 32 decimal, and stores it in this D1 pointer, which points into screen memory. So it's just a blank space, and it just loops through, and then it does a call here to this JSR E4DA, and that sets the color memory, and that's actually a patch back from kernel version 1. This is patching over, and that's why there's this NOP here, because I think originally there were 4 bytes here. They put a 3-byte change, and they just had to pad it out with a no operation, then decrement Y and branch of plus. Okay, so we can look at that, what that does in a moment, but we can just check before that. What we'll do is here is their patch, where you can see this is exactly the same, puts the blank space in. But what they've done is load A with 1, which is the color white, and store it in color RAM. And by these routines up here, D1 points to screen RAM, and F3 and F4, both of these are 16-bit pointers. F3, F4 point to the corresponding color RAM location at D800. There's an extra 1K of nibbles that store the color of that particular cell. So they're saying it always to white, and that's what kernel version 1 used to do. But kernel version 2 had this misguided approach here, JSR E4DA. Okay, so we can see what the fix is. Now they're going to set color RAM always to white. Now, if the background happens to be white, then you'll still have that invisible problem, but at least most programs this will fix. At least you'll have a white character and it'll be visible, as we saw when I did the poke 1024. Okay, so to make that clear, these are the 4 bytes that were poked in here. Now, interestingly, this isn't the same as what kernel version 3 did. If we look at that routine up above, E4DA, this is kernel version 2's buggy way of setting color RAM. If we disassemble here, it's just these 3 lines. So what what kernel version 2 did was actually load the background color. That's the hardware register that controls the background color. Like right now it's black because it's color 0. D021, it loads it, and that just puts that into the character cell for color RAM. So no matter what your background color is, it's going to be invisible when you poke to screen RAM. Of course, the program side fix, every time there's a poke to screen RAM, also poke to color RAM. But many C64 programs did not do that. And the reason print still works is that print does also poke to color RAM every time a print is issued. Well, at least when it's a printable character. Okay, so the way this is fixed in kernel version 3, if you're curious, is instead of loading from the background hardware register, which really isn't a good idea, it loads from location 0286, I believe, and that is the current cursor color. Okay, and that's a much more sensible thing. It makes sure that the screen is cleared to the current cursor color, and it will much more likely be visible that way. Or rather, the whole screen is cleared, like the line is cleared. That's what this routine does. Okay, so that's the 4-byte patch in the kernel. I'll switch back to the ROM. Okay, now this is the single byte patch. Let's bring both of them up. Okay, and the only thing that's been changed here is right here. Now this is in the reset routine. You know, I said that the patch manages to survive stop restore, and that's because of this little patch here. This is where location 1 is set, and I'm not totally sure why they used E here, but anyway, the important bit is these bits here. Just like you see here, I've been changing it to 3.7 to show the ROM. In the ROM version of the code, it's setting location 1 to 7 for that low nibble. Normally when you hit stop restore, it forces the ROM back in. And you see their little patch here. All it's doing is changing that nibble to 5 and storing it in. And you see that just matches here. The same 5 that we used to reveal the RAM, the patched RAM, well, it's just enforcing that to go back in. So it's very simple. They've made it impervious to stop restore. So that's pretty cool. That makes it much more of a real patch. It's not until you actually power off the computer or use an actual physical reset switch that you would get rid of this through normal use. I mean, you could poke that out manually, I guess, if you wanted. But okay, so that's both of the kernel patches that it does. Next, we'll look at the basic patches. So just again, switching back to the ROM from B384 to B39B. So that's the original. And here's the patch. Now you notice I didn't print as many lines. Well, that's because you start up here, set carry, you can see these match. Load A with 3.3, subtract carry with 31, transfer A to Y. And now where the original ROM has a load A 3.4, instead there has been a 3-byte patch applied, just making it jump to BF53. So I've demonstrated this other times. A lot of the time in a patch, if you can't fit it on top of the existing ROM, like you have to insert a byte or whatever, or you have more code than will fit, then what you often do is just insert a jump or sometimes a branch to a whole different area, and that's where you actually apply the patch, and then you make sure you jump back after. So that's why a lot of time with patches, there's actually 2 sections. One is the actual fix, the code that really does something, and then the other is just a little jump, 3 bytes, to allow that code to be executed. Okay, so that's that 3-byte patch we were talking about. That's all it does, is jumps to some code at BF53. Okay, what's that BF53? If we look at the ROMs, we'll see that this is actually a big empty, it looks like it's filled with the instruction TAX, transfer A to X, but that's just incidental. It's actually just filled with AA, which is just a simple binary pattern of 10101010. And a lot of the time, that is the fill byte in a ROM. If it's not being used, it'll just have a pattern. And I don't know about other companies, but Commodore often used AA. Somebody who knows more about hardware would say if there has any particular significance to that, apart from it just being alternating ones and zeros. Okay, so here's a big empty piece of ROM. Well, big, whatever it is, 18 bytes or something. At least it's unused in kernel version 2. I think kernel version 3 fills more of that up. Anyway, too many bunny trails today. Okay, so if we switch to the patch version, though, we'll do that same range. BF64. Okay, so this is what it looks like patched. All right, so these are the 18 bytes that were poked in that loop into memory. Now, if you have a good memory, this will actually look very familiar because it's what we were just looking at. Okay, so just to reiterate, this is the ROM. This is the patched RAM in that same location. Now, if I switch back to the ROM, but disassemble where the jump patch is again, so not at BF53, but back at B3-8D to B3-9B. This is the ROM, this is the RAM, and you see that they are identical. 34, 32, 0, 0D, 62, 63, 90, except the patch has a set carry and then the jump, and this one does not have a set carry and the jump is slightly different. So the patched one, the order is reversed from normal, so just so it's clear, set carry, and we're jumping to BC49 instead of BC44, so it's 5 bytes later. So it seems a little strange to me that the patch is all this is the ROM code that was already there. Now, I understand still having to do the patch because you want to add a set carry. You can't just do like an insert in a ROM. Everything else has to stay in the same place. So I understand why the patch was done, but I don't understand why so much of the ROM was carried exactly when really this is the only changing bit down here. Hey, maybe we'll do something about that later. Okay, but what does this do? Basically, this is patching the free command. Obviously, that's why we're patching the basic. Okay, so let's look at this free command in more detail. Let's have to switch back to the ROMs, and then we will disassemble B384 to B39B. Okay, so this is the original free routine here. Just quickly go through this. When you call free, this part actually calls the garbage collection routine. And Microsoft Basic has dynamic string handling, and over time, it's allocating string memory, but then those strings aren't needed anymore. So every once in a while, you need to do something called garbage collection, which even modern languages do. And that's what this calls. And it just goes through and discards all the old unused strings and kind of compacts the remaining strings together, freeing up some memory. Garbage collection happens automatically on the Commodore 64, but you can trigger it early by calling the free function, FRE, and then any parameter. You have to give it a parameter. It's just a dummy parameter. Okay, so that calls garbage collection. And then after that's done, it just is going to subtract two 16-bit numbers. Locations 33 and 34 are something called free top, which is basically the top of free RAM, and that defaults on the Commodore 64 to A1000, where the basic ROM is. There's RAM right up to there, and normally that's all free for basic use. And strings are formed up at that top of memory, and they work their way down. This is the top of RAM, essentially the top of the free area, and this is the low byte of it because it's an 8-bit processor. It's a 16-bit value, so you have to do it in 2 steps, but basically it's just going to load the top and subtract that from the bottom of RAM, which has the kind of dumb label of str end, string end, but really that's just the lowest that strings could go. More accurately, it marks the end of the basic program, or even more accurately, it marks the end of array RAM if you're using arrays in your program. So basically on the Commodore 64, you have your basic program that starts down at the low end of memory at 0801, and the basic code uses the RAM after that. Then wherever your end of your program is, when you run, then you have the space from the end of your program to the top of basic where the ROM is. Strings are filled in this area, and arrays use the space in between. If they meet each other, then you run out of memory and your program stops. So really it's just subtracting these two differences. So 33, subtract 31, store that in the Y register for later, that's the low byte, and then subtract the high byte of both. Load X was 0, just means that we're going to look for a numeric result. Microsoft Basic does this often. This location D indicates whether it's a numeric or a string calculation that's going to be done next. So this is numeric. Store that in D. Next, that 16-bit value is put into 6.2 and 6.3. Now, this is part of the floating point accumulator that Microsoft Basic keeps. So it's putting the 16-bit remainder from that subtraction, calculating the free RAM, putting it directly into the floating point accumulator. This is kind of hacky, but this is this is how it works. This is the actual ROM code. This isn't even the patch. And then X is being loaded with 90 hex. Now that's actually an exponent for the floating point numeric system. So I've still been meaning to do like a full floating point episode sometime. But essentially, that exponent means that there's an exponent of 10. It's 10 above 80, 10 hex, and that is 16 decimal. So essentially, it's saying that the value going in here is a 16-bit value. It feels kind of hacky to me, but this is how it works. And this is essentially converting the integer result of this subtraction for the memory, converting it back into a float, which is what Microsoft Basic uses throughout the ROM. It doesn't have true integers. Whenever it does calculations, it's doing them based on floating point. And then it's calling this routine BC44, which is partway into the sign routine, that is the function sign that returns a 1 if the number is positive, a -1 if it's negative, and a 0 if it's exactly 0. So it's kind of repurposing that function because it essentially has an integer to floating point routine. If we look at that real quick, okay, it's doing some funny business here. So basically the free routine is just stuffing that 16-bit value into the floating point and tweaking numbers so that it is a legit floating point value that can be returned to whatever called. And that's what happens right here. But this is the bug, is that when this code was first written, it was assumed you would never have more than 32K of RAM. It actually flips the sign here. It does this exclusive OR FF, and that inverts the value that's returned. And that's why you end up with that negative value normally in free. Okay, so what that patch does, as we were looking at, instead of jumping to BC44, it sets carry, which is what this bit does. It inverts it and rotates the value, so carry is appropriately set. Instead, the patch sets carry itself and jumps to here, to BC49, and skips that whole inversion thing. And the end effect is that instead of this code returning a signed 16-bit value, it now returns a unsigned 16-bit value, which allows the free routine to return a value greater than 32 kilobytes. So, thus fixing the bug. Okay, so I think I neglected to show that free bug, but there it is. I had that number 26627. Okay, so without the fix, just one more time to emphasize it. Print free 0 returns this goofy negative number, and poke 1024 puts that invisible A in the top left corner. There it is. And by loading up that patch, I wish I had called it just plain fix, but anyway, fix 3. We'll run that. There we go. Okay, so now with the patch in place, we can print free, and we get 38909 bytes free. If you're wondering why it doesn't say 38911, I did a whole video about that too, which I'll link to in the video description. Where'd those 2 bytes go? And I can't poke 1024. Well, I can, but it's just going to change that R to an A. You see, once you printed there, then it's okay. So what I'll do instead is I'll poke 106339. This should be in the top right corner. Okay, so you see that works there. Or here I can even poke the bottom corner, 2023. That was a good year. There, you see how it's appearing now? That's because it's fixed. It's not invisible. Okay, that is CBM fix. I think there might be even more to say about this another time, but that is enough for today. Thanks to my patrons for their support. Thank you for watching, and we'll talk to you next time.
I got sent to computer camp. Every day I'd walk to the college. We'd go to program on the terminals, learning basic code Fortran. It was pretty fun. I learned a thing or two. Lasted a week during summer holidays. Next time they offered computer camp, they changed it to computer and sport camp. So we program in the morning, but then play sports all afternoon. Somebody